Hello, welcome back. This is our video solution to problem 10 from Superquiz 3. In this problem, we're going to be finding counterexamples, right? Or examples if you like. We're going to be trying to find examples of ring structures that satisfy certain properties and not other properties. So let's jump right in. For example, part A, we're looking for a commutative ring that is not a field. So the problem here, right, we need to know what distinguishes the commutative ring from the field. And the important difference is in a field, every element is invertible. So we need to find a commutative ring where we know there are some examples of non-invertible elements. And a very easy one is going to be the integers. So the integers do form a commutative ring, and 2 is an example of a non-invertible element. So 2 is a non-invertible element. We know that the multiplicative inverse of 2 is 1/2, which is not an integer, right? So we know the inverse is 1/2, which is not an element of z. Since there's a non-invertible element, of course, 0 never counts, right? Like even in a field, 0 is not invertible. Since we have a non-invertible element, which is not 0, this implies z is not a field. Okay, so z, not a field. All right, how about B? B, we're looking for a non-commutative ring. Actually, all of the examples in class that we've been playing with feel like they've been very, very commutative. But there is one example that is non-commutative, and that was the matrix rings. I mean, this is not the only non-commutative ring, don't get me wrong here, but from what we did in class, matrix rings are a wonderful example of non-commutative rings. So we, for example, could look at the 2x2 matrices with entries in, well, we could do the real numbers or let's just do the integers. So let's give an example of two matrices that don't commute. And remember, when we talk about a ring being commutative, we're talking about under multiplication. Under addition, all rings are commutative. So what we're going to do is just write down really just some random matrices that don't look like, oh, I don't say like a diagonal matrix, right? Because that actually might work. So let's just do something like, I don't know, 1, 2, 3, 4. And then we'll multiply that by, how about 5, 6, 7, 8. Okay, maybe those numbers get a little too big. Let's see, so we get 5 plus 14 is 19. And then, you know what? I don't even want to fill in the rest of the stuff. Okay, there's more stuff coming, but let's turn this around. 5, 6, 7, 8 times 1, 2, 3, 4. And I go to the upper corner and I get 5 plus 18, which is 23. Now, there are other numbers and we could work them out, but it really doesn't matter. Because two matrices are the same if and only if they have all the same entries in the same positions. And here we have a 19 and a 23 in the upper left corner, so these are not equal to each other. So this is a non-commutative ring. All right, part C. We're looking for a commutative ring that is not an integral domain. So to be an integral domain, you need to satisfy this zero divisor property. Namely, if you take two non-zero elements, their product should be non-zero. So we have a wonderful collection of examples that all look like z mod nz. And all we need to do is take a non-prime number. So if we take, for example, z mod 6z, then inside here we have 2 and 3. And as usual, we use these to denote the equivalent class of 2, but we're being lazy. We know that 2 times 3 is congruent to 0 modulo 6. But 2 and 3 are not 0. Right? 2 and 3 are not 0 mod 6. Therefore, we have 0 written as a product of non-zero elements, and hence z mod 6z is a commutative ring, but not an integral domain. Okay, finally, we want a commutative ring that does not have a multiplicative identity. And this is probably the trickiest problem on here, although the answer is quite simple. So all of the rings that we've been playing around with, matrix rings, integers, Gaussian integers, Dedekind integers, modular integers, they all have a multiplicative identity. What could you do to get rid of it. And what it comes down to, right, is why don't we start with a commutative ring that we know, something easy like, say, the integers, and let's try to find a subring of the integers that omits the identity, right? We know the multiplicative identity is 1, so can we build something which is closed under both addition and multiplication, and which doesn't contain the identity? And if you've been paying close attention during the more recent lectures where we talked about ideals, that actually gives us a good idea. We can actually take any proper ideal. So for example, we take all the multiples of 2. So this is closed under addition and multiplication. If you add or multiply two multiples of 2, you again get a multiple of 2. In fact, all of the ring axioms are going to be satisfied. Of course, it's contained in Z, so it's commutative, but there is no multiplicative identity. Right? What do you multiply 2 by to get back to 2? Well, it's got to be 1, but 1 isn't in here. So 1 is not in 2Z, and there is no multiplicative identity in this ring. Now, there is a little subtlety right there. In the integers, it's not going to be a problem, but if we look in certain modular integer cases, we actually can find subrings that don't contain the multiplicative identity 1, and yet those subrings actually still have a multiplicative identity. In fact, let me give you an example. So let's go back to Z mod 6Z. So Z mod 6Z, which we can write down a set of representatives, 0, 1, 2, 3, 4, 5. It has a subring we get by taking the ideal generated by 2. So this will be all of the multiples of 2. Or we could also write this as 2Z modulo 6Z. So we take all the multiples of 2. And when we do, we're just going to get even numbers out of here, right? So 0 times 2 is 0, 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6, which is 0, so we're back here. 4 times 2 is 8, which is 2, and 5 times 2 is 10, which is 4. So actually, we just get these 3 even representatives. All right, and if I add any two of these together, modulo 6, I end up with one of these. And if I multiply any two, well, we've already seen 2 times anything works. How about 4 times 4? Well, that's 16, which is 4 again. Okay, so this is actually a subring, even an ideal. It's a subring of Z mod 6Z. So it's a ring. It's a commutative ring. And it doesn't look like it has the multiplicative identity because, well, up above, right, 1 is the multiplicative identity for Z mod 6Z. But something really funny happens here. If I multiply 0 by 4, I get 0. If I multiply 2 by 4, I get 8, but mod 6, this is 2 again, right? This is all congruent, right? Mod 6. And if I multiply 4 by 4, well, that was 16, but mod 6, that's also 4. Notice the common factor here of 4, and then look on the left and the right, you actually get the same values out. So even though 1, the multiplicative identity in Z mod 6Z, is not in 2Z mod 6Z, there is still actually a multiplicative identity. So 2Z mod 6Z has multiplicative identity, but it's equal to 4. How wild is that? All right, but if we go back to the integers, we're not going to have this problem because we don't have this modularity property that would mess things up. All right, when you take a number not 1 and multiply it by something, it's either going in absolute value, it's just going to get bigger. All right, so we don't have that problem over here. We could, of course, used any number other than 1 and had this exact same situation come out. All right, hopefully this helps you find some more of your own examples.